last episode, we have seen some of the important physical and chemical properties of the first row transition metal ion. Among these, we have seen the densities, melting point, hardness, ionization enthalpy, electronegativity, atomic and ionic radii, and in the last we have seen the reactions of the transition metal ion with the water and the acid. In this lecture, I am planning to introduce to you two important properties of the transition metal ion, namely the alloy formation and the variable oxidation state possessed by transition metal ion. One of the very important property of the transition metal ion is in the formation of alloy. These metal ion can easily form alloy because the atomic radii or atomic size of these metal ion is almost same, and therefore, in the crystal lattices one metal ion can be easily replaced by the other metal ion. The common alloy formed by the first row transition metal ion is brass, bronze, stainless steel, etc. All of you are aware that brass and bronze are the example of a alloy formed by the copper, while stainless steel is a mixture of chromium, nickel, iron, etc. There are mainly two types of an alloy formed by the transition metal ion: substitutional alloy and interstitial alloy. The first one is the substitutional alloy. In the substitutional alloy, the random replacement of one metal ion by the other metal ion in their crystal lattice occur. For this purpose, both the metal ion should completely miscible with each other and they should form a continuous range of a solid solution. Only few metal form this type of a continuous solid solution, and therefore, Hume and Rothery has shown that for complete miscibility the following three rules should be applied. These rules are also known as Hume-Rothery rule. According to this, the two metal must be similar in size, at least their metallic radii must not differ by more than 14 to 15%. Second rule says both the metal must have the same crystal structure. Third one, the chemical properties of the metal must be similar. In particular, the number of valence electron should be the same. If at least two of these three rules is followed, then the substitutional alloy formation will occur. Otherwise, substitutional alloy formation is difficult. Another important compound or alloy formed by the transition metal is interstitial compound or interstitial alloy. In this alloy, in the crystal lattice of the metal, some of the metallic atoms is randomly replaced by the non-metallic small atoms like hydrogen, carbon, boron and nitrogen, etc., to give away the interstitial compounds. They are usually non-stoichiometric and neither typically ionic nor it is covalent. The example of interstitial compound or interstitial alloy includes TiC, Mn4n, Fe3H, VH.56 and TiH 1.7. In this compound, you can see some of them are stoichiometric while some of them are non-stoichiometric. So, this is how in the crystal lattice of iron, some of the iron molecule is being replaced randomly by the small atoms like a carbon. This interstitial compound principle having different physical and chemical characteristics. Some of these are, they are very high melting point, they are higher than those of the pure metal ion sometime, they are very hard, retain their metallic conductivity even though the some of the metal is being replaced by the non-metallic compound and they are chemically inert. This interstitial compound and other substitutional alloy are very useful compound and find wide use in many day to day life as well. The various oxidation state of this element can be very easily summarized because it form a regular pyramid kind of a structure. Several of the element have also possess 0 valent and low valent state, particularly 0 valent state and low valent state compounds are stabilized with the pi bonding ligand such as carbonyl and dipyridyl. This figure shows the pyramid change in the oxidation state of the first row transition metal ion. As you can see, scandium have only one oxidation state, but the manganese can have as many as 6 to 7 oxidation state, and its changes gradually increases as we go from scandium to manganese and gradually decreases as we go from manganese to zinc. Some of the stable oxidation states are also is highlighted by the different color in this diagram. The meaning of a stable oxidation state is there is a not much change in the oxidation state at room temperature by air or in the solution. One of the striking feature, as I said, is the occurrence of this metal ion in variable oxidation state. The 3d and 4s electron are very similar in energy and both are available for bonding. So, the element of the first series forms ions of roughly the same stability by losing different number of 3d and 4s electron. So, these are some compounds, particularly oxides, chlorides and some other compounds of transition metal ion. You can see that these compounds exist in +1 to +7 oxidation state. In +1 we have a cuprous oxide and cuprous chloride. Nickel can have +2 oxidation state as well as +3. The +3 nickel oxide, hydrated nickel oxide, is having composition Ni2O3. Vanadium can possess various oxidation state ranging from +2 to +5 in their chloride and oxides. Same is with the chromium and manganese. They also possess a variable oxidation state. Worth to mentioning is the permanganate ion Mn2O7 having +7 oxidation states. This is again the possible oxidation state of the first row transition metal, some of which are very stable. Almost all of the transition metal ion except scandium can possess +2 oxidation state. Scandium and zinc do not exhibit various oxidation state. Scandium has the only +3 oxidation state which is stable at room temperature. The reason for this stable oxidation state is because electronic configuration of this scandium is like argon after removing the 3 electron. Similarly, the zinc can possess +2 oxidation state only because by removing 2 electron, zinc acquires the stable electronic configuration having argon 18 3d10. All the elements of the first transition series except scandium can show +2 oxidation state. So, the most common oxidation state possessed by the first row transition metal ion is +2. All the element of the first transition series except zinc can also show +3 oxidation state. Manganese has the highest oxidation state of +7, particularly the example is permanganate ion. In permanganate ion, manganese is having +7 oxidation state. The +7 state of the manganese does not mean that all the d 3d and 4s electron are removed from the manganese to give Mn plus 7. Instead, manganese is forming covalent bond with the oxygen atom by making use of the half filled orbital. So, this is a structure of the manganate ion in which the manganese is involved with the bonding with the oxygen. If I give you a task to draw the structure of permanganate ion, how will you draw? This is what is the structure of permanganate ion, in which two manganese is joined together by oxygen having one oxygen common. For the element after the manganese, there is a reduction in the number of possible oxidation state. The 3d electrons are held more firmly because there is a decrease in the number of unpaired electron, and also there is an increase in the nuclear charge. The relative stability of the various oxidation state is correlated with the stability of the electronic configuration. Let us see the example of manganese having two different oxidation state, Mn2 plus and Mn plus 3. Now, here the major factor is lying in the electronic configuration. Manganese plus 2 having 3d5 electronic configuration, while 3d4 will be in case of manganese 3 plus. Of course, 3d5 is more stable, and that is why manganese 2 plus is more stable in the aqueous medium. Same is the case lying with the Fe, Fe plus 3 having 3d5 electronic configuration, while Fe2 plus will be having 3d6 electronic configuration. As the 3d5 configuration is more stable compared to 3d6, in the aqueous medium iron plus 3 will be more stable compared to iron plus 2. As I said, the major factor is the delta H0 hydration. This stability of the other various oxidation state is also true in case of a zinc. Zinc possesses two different oxidation state, namely zinc 2 plus and zinc 1 plus. As the zinc 2 plus having 3d10 electronic configuration, which is more stable compared to the 3d10 4s1 electronic configuration, zinc generally occur in the aqueous solution in 2 plus oxidation state, and which is the stable oxidation state in case of a zinc. Next comes the compound of the vanadium. Vanadium can exist from plus 2 to plus 5 oxidation state, and these ions of different oxidation state are formed by the vanadium. Also, they show distinct color in the aqueous solution. This is how the color of the ion changes as the oxidation state changes in case of a vanadium. Vanadium 2 plus is violet in color, 3 plus is green in color, 4 plus is blue in color, while vanadium 5 plus is having yellow color. This color also changes with the change in the pH. That is to say, in acidic medium, vanadium 5 state usually occurs in dioxo vanadium ion. Vanadium 4 state occurs in case of an oxo vanadium compound, that is VO2 plus in aqueous medium. However, in the alkaline medium, the stable form of a vanadium 5 is VO3, that is metavanadate, and also the oxovanadate, that is orthovanadate, that is VO4 3 minus is also occurring in a alkaline medium. Compounds with vanadium in its highest oxidation state is, that is plus 5, which is strongly oxidizing agent, and the lowest oxidation state of a vanadium is 2 plus oxidation state, which is of course strongly reducing agent in the nature. Easily oxidize to higher oxidation state when it is exposed to the air. Therefore, the interconversion of the common oxidation state of the vanadium can be very easily carried out in the laboratory. When you do the experiments, particularly on the qualitative inorganic analysis, you will find that there is a change in the oxidation state of the vanadium with the change in the pH. As we know, along in group 2, first two group, that is group 1 and group 2, the pH is acidic and pH changes to the basic medium as we go from group 3, 4 and so on, and therefore, there is a color change is found in case of a vanadium compound. The most convenient starting material which is given in form of a salt in the qualitative inorganic analysis is the ammonium metavanadate, which is a white color solid, and in ammonium metavanadate vanadium exists in +5 oxidation state. How this interconverted to the various vanadium species is shown in this figure. Vanadium 5 can exist as a cation also as well as anion. Now, as I said, the interconversion can be achieved in the qualitative analysis based on the pH of the medium. In the acidic medium, vanadium have color yellow, while in amphoteric medium we have a orange color. However, in the basic pH, vanadium can exist in yellow and as well as colorless compound. Now, this interconversion is also depends not only on the pH, but is also changes with the medium. This is again how vanadium 5 species can exist in the water and undergo hydrolysis to give VO4 3 minus ion, that is oxavanadate ion. The reaction is favored in highly alkaline solution. So, we have vanadium in VO4 3 minus, that is orthovanadate ion. Similarly, chromium can have chromate ion, manganese have manganate ion. Let us draw the structure of this vanadate, chromate and manganate ion. The structure of vanadate is something like this, chromate is this, and manganate ion already we have seen earlier the structure of the manganate ion. In the alkaline solution, how this is vanadium ion changes, that is also shown in this figure. Now, this is what the structure of metavanadate ion in 3 dimension, it can have this type of a structure. In the acidic solution, particularly with zinc powder, you can very easily convert the vanadium +5 into vanadium +2, that is you can carry out reduction sequentially to form vanadium +5 to vanadium +2. This slide shows the color of the aqueous solution of the compound containing vanadium in 4 different oxidation state. The first one shows the vanadium in +5 oxidation state, second one in +4, third one in +3 and the last color is vanadium in +2 oxidation state. Same happens with the manganese. Manganese can also have a variable oxidation state from +2 to +7. The most common oxidation state of the manganese in their compound is +2, +4 and +7. This slide shows the various colors of the manganese compound along with the different oxidation state. Manganese 2 plus is faint pink in color, +3 is dark brown, +4 is black, +5 is bright blue, +6 is greenish color, while +7 is purple in color. This slide shows the compounds of manganese ion having different oxidation state starting with +2, +3, +4, +6 and +7. You are aware about the compound of the chromium also. Chromium can also exist in various different oxidation state, particularly the structure of chromate and dichromate is worth to note. You are aware about the chromate and dichromate ion. as you are analyzing it in qualitative inorganic analysis. Manganese also can have +2 to +7 oxidation state, we have just seen in different color. It is in acidic medium, you can have manganese in +4 oxidation state and it can be reduced to 2+. In the alkaline medium, manganese is having +6 oxidation state. So, in general, in this lecture we have seen the two important property of the transition metal ion, that is their ability to form alloy, that is different type of an alloy like brass and bronze and interstitial compound formation, and also we have seen the variable oxidation state possessed by this transition metal ion. In the next lecture, I am going to give you some more important physical and chemical properties of the transition metal ion.